In the previous video, we have studied the basic concept of algorithm analysis. To summarize, we said we have two types of algorithm efficiency we care about: time efficiency and space efficiency. And also called time complexity and space complexity, right? And we said both they use the same technique to measure the asymptotic order of algorithm growth. Both is the function of input size, although they are from different perspectives. One is from the time perspective, the other is from memory space perspective. And let's use the time complexity as an example. With time complexity, it is a function of input size, measuring how fast the algorithm could be as input size goes to infinity, right? And then in the previous video, we also talk about give you algorithm. We have to first identify basic operation. Second, we have to count the times, how many times this basic operation has been executed. And such that we could write the function for different code. And sometimes we care about, we have two methods, we have two algorithms, we care about which one is better. And then we see, once we have a function, the runtime function, the runtime growth function, which is based on the input size. And for example, here we have three examples. Although we have different formulas, but we care more about which group they are cast into. Can this different runtime function can be cast into the same group or not? Now this is we talk about asymptotic order of algorithm runtime growth function. And the idea of this asymptotic order, it is we want to compare the different algorithm runtime. We want to compare the different algorithm. We want to check this algorithm can be in the same efficiency group or not. And we think most important is we check the order of growth within the constant multiplies as n goes to infinity. This we call asymptotic order. And also it's corresponding to we check how much faster will algorithm run on computer, that is twice as fast. And for the space complexity, we ask a question, how much longer does it take to solve a problem of double input size? And from here, we give you this formula. We want to check that to find out the coefficient is not so important. Let's take a look. Let's say we have one growth function of the one specific algorithm is Tn equal to Cn. If we double input size, then we have T2n equal to C times 2n. When we check the growth rate, we check the growth ratio. So we have T2n divided by Tn, we have 2. This is a double input size. And from here we see this C, we really don't care about what is the specific value of this C, because we care about growth ratio when the input size double as n going to the infinity. And let's take a look at another growth function. Tn prime is equal to Cn squared. And when we double input size, we have T2n equal to C times 2n squared. And then when we check the ratio of this growth function, T2n divided by Tn, we have number 4. This number 4 doesn't relate to this C. It means coefficient, this C, this number of this C, this specific free variable C could be any number. And in this growth ratio or growth rate doesn't depend on this coefficient. And here we also take a look at one examples here. Take a look at this table. This gives us the values of several functions important for analysis of algorithm. We want to check, give you algorithm, we want to check this algorithm can be cast into which type of efficiency. So for example, take a look at the first row, and he gives us the different runtime growth function. Log to n, log to n square, n cube, to the power of n factorial. We want to check when n increase, what is the growth ratio for each of these functions? How much faster for each function when n increase? Let's take a look at last row. And from the last row, we can see when n close to 10 to the power of 6, 100,000. In that case, the runtime of log to n corresponding to 20 milliseconds. For another group, n, it is corresponding to 10 to the power of 6. And n log to n corresponding to 2.0 times 10 to the power of 7. From here, we can see when n increase, the growth, the runtime, the algorithm growth rate is really increased a lot. If they belong to n to the power of n cube. So we say give you algorithms which solve the same type of problem, a way of comparing function, the way of judge which algorithm is more efficient, or the way to compare function, the growth function, is to ignore constant factors, ignore the coefficients, and also smaller input size. We use a specific notation to check the asymptotic order of the growth. Big O notation. Big OGN is defined as class of a function fn that grow no faster than gn. It also corresponds to big OGN is the group of all the functions with a lower or same order of growth as gn as n goes to infinity. Theta gn corresponding to a group of functions fn that grow at the same rate as gn. Theta gn is a group of all the functions with the same order of growth as gn when n goes to infinity. Omega gn is defined as class of function fn that grow at least as fast as gn. So here we use this picture to tell us what does mean, what does the intuitive understanding of big OGN. Big OGN corresponding to this upper bound, corresponding to a group of function which is upper bound by the gn. For example, here this the first curve corresponding to gn, and the second curve corresponding to tn. We say it doesn't matter how n increase, the tn always upper bound by the gn. So this is we talk about big OGN. If we have tn belong to big O, gn is corresponding to when n increase to infinity, tn the growth rate function when less than the growth rate function gn. This is big omega. If we have tn belong to the group of big the omega gn, in that case we say this function is lower bound by gn, Big omega Gn corresponds to the group of function which is upper bound by the Gn. It also corresponds to, doesn't matter how n increase, the runtime of Tn will never lower than the runtime of Gn. The growth rate will always smaller than the growth rate of Tn will always bigger than Gn. And opposite way, Gn, the growth rate of Gn will always smaller than Tn. And we see this is very interesting. The Tn belong to big omega Gn, also corresponding to Gn is belong to big O Tn. Here we showed one picture about the big theta. When we see Tn belong to big theta Gn, it corresponding to Tn is upper bound by Gn, C1 Gn, upper bound by Gn, and also lower bound by the Gn based on different coefficient C1 and C2. Now let's take a look at this example. Let's say 10n is belong to O n squared. Do you think it's correct or not correct? We see this is correct. The reason it is 10n is upper bound by n squared. And 5n plus 20 is belong to On. This is also good. 5n plus 20, which is belong to the big theta O, big theta n. Big theta n also corresponding to this function upper bound by the Gn, also lower bound by the Gn. There is very beautiful property in the asymptotic order of growth. We see if Fn belong to OGn, if and only if Gn is belong to big omega Fn, and also this asymptotic order of growth conform to the transitive relationship. If Fn belong to OGn and Gn belong to OHn, then Fn belong to OHn. If F1n belong to OG1n and F2n belong to OG2n, then F1n plus F2n belong to O maximum G1n and maximum G1n and G2n. Some students may ask, how can we know which function has a higher asymptotic order? We see this is the way we can use the limit function. Limit Tn divided by Gn when n close to infinity. We see the results if equal to 0. In that case, the growth function of Tn has a smaller order, asymptotic order than Gn. If the result is constant, then in that case, Tn and Gn, they both cast into the same asymptotic order group. If the result it is going to the infinity, in that case it means Tn will growing very, very fast compared to the Gn when n close to infinity. Take a look at this example, 10n versus n squared. With n squared has a higher asymptotic order than the 10n, right? You can count for that. And n times n plus 1 divided by 2, which is the same asymptotic order as n squared. And also why do people like to use limit function? Because sometimes it's very easy to do calculation. We say, we get, check two functions, check the asymptotic order of these two functions, Fn, Gn. We use limit n goes to infinity, Fn divided by Gn. If this one is hard to calculate, we can use the first differentiation for help. And we say this is equivalent to limit n goes to infinity, f prime first differentiation of n divided by g first differentiation of n. Usually, we just need to remember the first several important function group. But just in case if some interview they ask you for even more complicated, and then you can check for different compilation. And we said all the logarithmic function log an belong to the same class, theta log n, no matter what the logarithm base a larger than 1 or not. So it means we can ignore the base. All the polynomials of the same degree k belong to the same class. And doesn't matter how many sub-elements, so how many items included in this formula. And with all the polynomials of the same degree k belongs to the same class, which it is belong to big theta n to the power of k. Exponential function a to the power of n have different orders of growth for different a. If a is different, therefore they are cast into different asymptotic order group. And we see the order log n smaller than the order n to the power of alpha, and smaller than order of a to the power of n smaller than order n factorial, and smaller than order n to the power of n. For this one, we just need to remember that you can also use what we introduced the previous technique, use the limit function to check each specific pair. And sometimes we see if the runtime is constant, corresponding to the this algorithm, doesn't matter how this input size increase, they are always the same or similar steps they lead. It doesn't increase the runtime if the input size increase. In that case, we call this runtime, this time complexity, it is a constant. And we would like to write O big O1. And in this semester, we use a lot, and most likely we emphasize seven asymptotic order group, constant, logarithmic, linear, n log n, linear arithmetic, quadratic, exponential, factorial. This is the picture to show us this different the functions which cast into different asymptotic order in the previous slide. And from here, the x-axis corresponding to input size, y-axis corresponding to the runtime. Each curve here corresponding to the runtime growth function over the input size. And we can see here the constant has less runtime when the n doesn't matter how n increase. And the logarithmic has less runtime compared to linear, given the same input size. And the linear, that the curve has less runtime. And then the linear arithmetic given the same input size. And also it corresponding to different functions, different specific statements. You can take a look here. For example, the first line here, a equal to b plus c. In that case, it will never increase the runtime, even if you increase the input size. And then this is the second one corresponding to logarithm. And in this loop, the n it is a count variable. If n larger than 1, you decrease n by half. And then this looping will stop only when n equal to 1 or smaller than 1, right? So in that case, definitely need to have log n iterations. The runtime is belong to log n group. And in the third row corresponding to linear runtime. So it means when we give you the code, we want to take a look at the code and count the times of basic operations rather than growth function, ignore the coefficient, ignore the lower term, asymptotic order term, right? Because we emphasize what is the growth ratio between the two functions when the n increases to infinity. If n increases to infinity, the lower asymptotic order term, compared to the highest, the asymptotic order term is really to become menacing. It could be ignored. Definitely, it makes sense to ignore that. Big O notation gives an upper bound on the growth rate of a function. The statement Fn is a big OGN means that the growth rate of Fn is no more than the growth rate of Gn when n goes to infinity. Usually we like to use big On because we want to check what is the worst case and what it is. It's just like in the real life, we prepare for the worst, we expect for the best. So this is big O, just like we prepare for the worst. We see our algorithm will level more than the growth rate function Gn. So this is very important. We want to say our algorithm is upper bounded by this group, this runtime, this algorithm runtime growth function. So we say that is that is the efficiency, that is the time complex group. To summarize that, for the non-recursive algorithm, the general plan for algorithm analysis cuts into different steps. First one, decide on parameter n of the growth function, right? To decide which one corresponding to what we talk about input size. Second step, identify algorithm's basic operation. Third step, determine worst, average, and best cases for input size n. Fourth step, set up a sum for the number of times the basic operation is executed. Simplifying the sum uses standard formulas and rules. Ignore the lower order sub-expression, ignore the coefficient of the highest order sub-expression. And in this algorithm analysis, when we count the times operation, especially emphasize the looping in the non-recursive algorithm, sometimes we have to use very useful summation formulas and rules. For example, this is the sum of number of ones. This is the sum of number of i's. This is this is sum up I square. And this is sum up a to the power of I. This is sum up ai plus minus bi. This is the combination of all the previous summation. So for this one, please, I would like I also post this slides in the Canvas, and these formulas we use a lot in the whole semester. I really would like you could print it out and bring it with you when you work on the assignment. And if you are interested in to say you want to prove that, and you can come to me or email to me, or tell me you are interested in that, then definitely we can provide another video to prove that. Okay, let's move on. Here we want to, in the remaining several slides, we want to practice how can you use this guideline. Actually, in the previous slides, we already practiced that, right? We already practiced how to find the basic operation, how to count the number of times the basic operation is executed. And we also practice how to write a growth function and to simplify the growth function. Now let's practice that. Take a look at this code, and I will find out what is the meaning of this code. This algorithm is named as maximum element. First, we assign element at the element in the location. In the first location is the first element. Assign the first element into maximum value and scan the whole array from the index 1 through index n-1, and we check if the current element it is greater than or greater than maximum value or not. If it's true, we reassign current element to maximum value. This looping will continue until we meet the last element. Then we return maximum value. We want to identify what it is our runtime growth function parameter. We say this is the n, right? This is corresponding to array length. What is the basic operation? The basic operation should be related to what you have the input size, right? So in that case, it makes sense. And in this case, you check each specific statement. And we also see here, basic operation also corresponding to that input size related statement, which make most contribution to the growth runtime function. So we see first row, maximum assigned to be the first element, which is a constant runtime, doesn't depend on the input size, right? And then check for the loop. This is the count-based loop. It will have n-1 iterations. In each iteration, it compare the current element with maximum value. In that case, we see here, this comparison has to be repeated for n-1 times, right? And check the next line, maximum value assigned to be current element. This is the statement if condition is true. If condition is not true, this will be ignored. So this reason we see that this line, the statement in the if body, you cannot use it as the basic operation, right? Because it's depending on, and it could be less, could be more. And also this is good for check best case or worst case of input instance. We will check a little bit later. And then in this one, we see the basic operation is comparison statement, ai larger than maximum value or not. And how many times this comparison has to be invoked? We say depending on number of iterations. If we have n-1 iterations, in that case, this comparison statement should have n-1 times. So in such a case, we see, okay, yeah, that's good. I'm taking a look at the description here. So we see, take a look at this one. We see best case. Best case, what is runtime for best case? And we see here, since this comparison statement has to be invoked in the n-1 iterations, and such that we ignore the lower asymptotic order 1, right? So we have big O(n). Best case big O(n), worst case also big O(n). The reason is comparison statement has to be run for each position of array. Let's take a look at average case. Assume the maximum value happens in any position A with the uniform probability 1 divided by n. We see the line 1 will take a constant runtime, line 2 and line 3, which comparison will take big O(n) times, and 3 we also take big O(n) terms, and these 2 and 3, then when we sum them up, we have O1 plus O(n) plus O(n) plus the runtime for the fourth row, the statement in the fourth row, because this statement really depending on, well, this maximum number stay, right? So in such case, we use the probability 1n sum up the probability times the position I. So in the total, this is what we have for the average. Yeah. So in that case, when you sum them up, we use the formula from the previous slides. We have the runtime, even for average case here, still O(n), big O(n). Okay. So we have several examples we left. If you're interested, you can take a look the slides and work on that. If you need, we can make another video. I think that's all for this part. In this part, we emphasize the algorithm analysis for non-recursive algorithms. So we emphasize the guideline for this analysis. First, we need to identify the growth function parameter, which is input size. Then we have to identify algorithm's basic operation, determine the worst case, average case, and best cases for input size n, set up a sum for the number of times the basic operation is executed. Then we have to simplify the sum, use standard formulas and rules, ignore the lower order sub-expression in the growth function, ignore the coefficient of the highest order sub-expression in the growth function. That's all. Thanks.